Hey there, in this video we are going to look at how we solve a system of linear equations using the substitution method. So to use the substitution method to solve a system of linear equations, we want to make sure that at least one of the equations has one variable fully isolated. Now that doesn't mean both of them have to, just one of the equations has to have it fully isolated. So either an x by itself or a y by itself or one of the variables if you're using different letters in that equation or equations. So if it doesn't already have a variable isolated, then we need to make that step to get the variable, one of the variables by itself in one of the two equations. Once we've done that, we can substitute the expression equivalent to that isolated variable into the other equation, and then we'll be able to solve like a basic linear equation. So let's take a look at an example and actually put this to use. So if I have the equation x minus y equals 3, and 2x plus y equals 9. These are both linear equations individually, and together they form a system of linear equations. So we are looking to use the substitution method. And to do that, we need one of the variables by itself. So looking at these two equations, my suggestion, and there would be three here, two preferable options, and then a third that isn't too bad. I would either get the x in this first equation by itself, or I would get the y in the second equation by itself. If you really wanted to, you could get the y in this first one by itself, but there is a negative in front of that y. So you are going to have an extra step compared to getting this x or this y by itself. So the reason I wouldn't suggest the 2x and really wouldn't suggest the negative y is because it's not just y or it's not just x. You have to actually get rid of the negative 1 in front of this y or the 2 in front of this x if I were to get those terms by themselves. So I'm going to go ahead and do the x right here. I'm going to just get that by itself. So I'm going to rewrite x minus y equals 3. To isolate that x, what we want to do is we want to get rid of the minus y. So inverse operations allows us to add y to one side and then in return add it to the other side as well. Negative y plus y is 0. So we just have x equals 3 plus y or y plus 3, however you want to do it. Now that I have this equation from the original and this equation, which is the first one, just rearranged, and now that I have that x fully by itself, I can use the substitution method. So I have x by itself. X is set equal to 3 plus y. What that means is those are equivalent values. So whatever x is, then over here we have 3 plus y that represents the same amount as x. So in this second equation right here, we are going to replace x with what it is equivalent to. So in this case, x is equivalent to 3 plus y. So we can put 3 plus y over here in place of x, and it will mean the same thing because those are set equal to each other here. So let's go ahead and write that out. So 2x is going to now be 2 times 3 plus y. And then we continue with the rest of the equation. So plus y equals 9. So again, I got in that first equation, I got x by itself. I plugged in the expression that x is equal to into x in the other equation. And then what I do is I just simplify, because you'll notice that I have an equation with one variable now. Because I have one variable, I can go ahead and distribute this 2. When I distribute the 2, I get 2 times 3, which is 6. 2 times y is plus 2y. And then I still have plus y equals 9. At this point, what I want to do is I want to go ahead and combine like terms. So 2y plus y. When I combine those like terms, I get 3y. So now I have 6 plus 3y equals 9. At this point, I want to go ahead and get my 3y by itself. So to get that 3y by itself, I do the inverse operations required. So in this case, 6 plus 3y. I would subtract 6 because 6 is positive. So subtracting 6 minus 6 is 0. But if I subtract 6 from the left side, I need to do it to the right side as well. So now I have positive 3y equals positive 3. At that point, I can go ahead and divide both sides by 3. When I divide both sides by 3, first of all, I chose to do that because 3 times y is already there. The opposite of times 3 is divided by 3. So this 3 and this 3 simplify to a 1 or cancel out, and we just get y equals 3 divided by 3 is 1. So the y coordinate of the solution to this system is 1. So we should always write our answer as an ordered pair, and it will be x first and y second. Now we do know that the y value is 1, so I could set up my ordered pair already and put a 1 in that y spot. If you want to make sure that you don't accidentally put it in the wrong place, you can do that as you go, or you can wait. It's up to you. So now we can go back to either of our original equations. It does not matter which one you go back to, but you are going to take that value that you got for whatever variable you solved for first. In this case, we solved for y. So I'm going to go back to one of these two equations, and I'm going to put a 1 in for y. So I'm going to choose the first equation, x minus y equals 3. So with that equation, we are going to plug in what we know y is equal to, and that's going to be this 1 that we just solved for. So x minus 1 equals 3. And now we just solve like a basic linear equation. Inverse operation tells us to add 1 to both sides so that we can cancel out that -1 and get just x on the left side. 3 plus 1 is 4. So 4 is the y coordinate. 4 is the x coordinate, and we already know the y coordinate. So 4 comma 1 is our ordered pair. Now, just a reminder, visually, this represents, if I were to graph these two lines, this would represent the point where those two lines cross, because that is the ordered pair that is part of both of those lines. So just a quick review for substitution steps. So first thing you want to make sure you have is one of the variables isolated. And it just has to be in one of the two equations. It does not have to be in both. It can be in both, but does not have to be. And then once you've done that, we plug in the expression equivalent to that isolated variable. And then once we've plugged in that expression into that isolated variable, specifically in the other equation, then we solve for that variable. Okay, whichever one we have in that equation. And then we plug back into the original to solve for the second variable. Okay, so those are our steps for our substitution method. So once we've, again, isolated the variable, or it's already done for us, we plug in the expression equivalent to the isolated variable, solve for the first variable, and then plug that into the original, one of the original equations, does not matter which one, to solve for that second variable. Now you can check your answer by plugging in that ordered pair. So in our last example, 4 comma 1, we could have plugged in 4 for x and 1 for y into both equations to check and make sure that it works in both.